Picture this: the entire universe, everything you see and know, began as a single flickering possibility, a ghostly dance of maybes before reality even existed. This isn't science fiction. It's the heart of quantum mechanics, where particles can be in two places at once, and reality itself is built on uncertainty. But what if I told you this quantum weirdness didn't just shape atoms or stars? It birthed the cosmos. The universe's very first moment might have been a quantum superposition, a state where all possible beginnings existed at once until something snapped it into the world we recognize. Today, we're diving into 30 mind-blowing theories about that primordial quantum leap. From parallel universes to cosmic holograms, these ideas don't just rewrite the story of our origins, they shatter our understanding of reality itself. Buckle up, by the end of this journey, you'll never look at the night sky the same way again. Now, let's peel back the layers of our cosmic origins with the first theory. Imagine the Big Bang not as a single explosive moment, but as a quantum flicker, a fleeting blip in the fabric of nothingness. Some physicists suggest the universe didn't just burst into being from a hot, dense point. Instead, it emerged from a quantum superposition, a state where every possible beginning existed simultaneously. Picture a cosmic dice roll, where the universe was both here and not here until chance, or some deeper law, collapsed the possibilities into the reality we inhabit. This idea ties directly into quantum mechanics, where particles routinely exist in multiple states until observed. If the Big Bang was a quantum event, it means our entire cosmos could be the result of a single, unimaginably rare fluctuation in the quantum void. No need for a cause, no need for a before, just the raw unpredictability of quantum physics birthing everything. The implications are staggering. If the universe began as a quantum fluctuation, it challenges our deepest assumptions about time, cause, and effect. Was there ever truly a nothing before the Big Bang, or just a sea of quantum potential waiting to snap into reality? This theory doesn't just explain how the universe began, it reshapes what beginning even means. And if quantum mechanics could spawn our cosmos once, who's to say it hasn't happened countless times before? The Big Bang might not be unique, just one bubble in an endless quantum foam of universes. Now let's stretch our imaginations even further with the second theory. What if the universe's first quantum superposition didn't just collapse into one reality, but instead branched into countless others? This is the mind-bending idea behind the multiverse. Picture the moment of creation not as a single dice roll, but as a cosmic slot machine where every possible outcome actually happens. Each spin births a new universe, each with its own unique set of physical laws, particles, and even histories. This theory takes the weirdness of quantum mechanics and scales it up to the grandest level imaginable. In the quantum world, particles exist in multiple states until observed. The multiverse idea suggests the entire cosmos did the same thing. Instead of choosing one path, the universe's initial superposition split into every possible path, like a tree with infinite branches. Somewhere out there, another version of you might be living in a universe where gravity is weaker, stars burn blue, or dinosaurs never went extinct. What's truly fascinating is how this bridges quantum physics and cosmology. The same rules that govern tiny particles could apply to the birth of reality itself. It's not just about parallel worlds, it's about the very fabric of existence being woven from quantum possibilities. And if this theory holds, it means our universe isn't special or alone. It's just one page in an endless cosmic library where every story that could exist does exist. The multiverse isn't science fiction, it's a serious scientific idea that forces us to rethink everything we know about reality. Now, let's take a step into a theory that flips our understanding of reality on its head. Imagine the entire universe, every galaxy, star, and even you, not as a three-dimensional space, but as a two-dimensional surface projecting an illusion of depth. This is the Holographic Universe Hypothesis, and it suggests that everything we see and experience might just be a cosmic hologram. At the heart of this idea is the notion that the universe's first quantum superposition wasn't just a fleeting moment. It was the foundation of a two-dimensional quantum surface encoding all the information needed to create our three-dimensional reality. Think of it like a movie screen. The images appear to have depth, but they're actually flat projections. In the same way, our universe could be a projection from a hidden, lower-dimensional layer where quantum superposition holds the code for everything. Physicists like Leonard Susskind have explored this mind-bending concept, showing how the mathematics of quantum mechanics and black holes support the idea. Black holes, for instance, seem to store information on their surfaces rather than their volumes, hinting that reality might work the same way. If this theory is correct, superposition isn't just a quirk of tiny particles. It's the very framework of existence, weaving the fabric of space and time from a flat quantum canvas. What's truly wild is how this reshapes our place in the cosmos. We might not be living in a vast, three-dimensional expanse, but rather on the surface of a deeper quantum reality. It's a humbling thought, one that challenges us to rethink not just the universe's origins, but the very nature of what's real. And if the holographic principle holds, it means the answers to the biggest mysteries of existence could be written in the quantum code of a two-dimensional world we can't even see. Now, let's shift gears to a theory that ties the mind-bending quantum world directly to the grand scale of the cosmos. Quantum decoherence might sound like an abstract idea, but it could be the key to understanding how the universe's first quantum superposition gave birth to everything we see today. Picture this: in the earliest moments of the universe, reality wasn't just one thing. It was a blur of countless possibilities, a quantum soup where every potential outcome existed at once. But then something happened. The universe began to expand at an unimaginable rate, a process we call cosmic inflation. And as it expanded, those quantum superpositions started to collapse like a fog lifting to reveal a clear sky. This is where decoherence comes in. It's the process that makes quantum weirdness, the ability of particles to be in multiple states at once, fade away, leaving behind the stable, predictable reality we know. Think of it like tossing a coin. While it's spinning in the air, it's neither heads nor tails, but both at the same time. Only when it lands does it choose a state. In the same way, the early universe's quantum fog landed on the reality we inhabit today thanks to decoherence. What's fascinating is how this connects to cosmic inflation. The rapid expansion of space didn't just stretch the universe, it also amplified tiny quantum fluctuations, turning them into the seeds of galaxies and cosmic structures. Without decoherence, those fluctuations might have remained trapped in superposition, leaving the universe a formless haze. Instead, they became the blueprint for everything, from the tiniest atoms to the largest galaxy clusters. So, the next time you look up at the night sky, remember, the stars and galaxies you see might owe their existence to a quantum coin flip that happened billions of years ago. It's a reminder that the universe's most profound mysteries often lie at the intersection of the unimaginably small and the cosmically vast. Now, let's dive into one of the most mind-bending ideas in quantum physics, John Wheeler's participatory universe. What if the universe didn't just exist on its own, but needed someone to observe it to take shape? Wheeler's observer effect flips the script on how we think about reality, suggesting that the universe's first quantum superposition couldn't settle into a definite state without a conscious observer. Think of it like a tree falling in the forest. We've all heard the question, if no one's around to hear it, does it make a sound? Wheeler takes that idea to the cosmic level. In the early universe, before any stars or planets formed, quantum superpositions were everywhere, a haze of infinite possibilities. But according to Wheeler, those possibilities couldn't collapse into the reality we know without an observer. It's as if the universe was waiting for someone or something to look at it before deciding how to exist. This isn't just philosophy. Quantum experiments like the double-slit test show that particles behave differently when they're being watched. When no one's measuring them, they act like waves spreading out in all possible paths. But the moment an observer steps in, they snap into a single, definite position. Wheeler argued that this same principle might apply to the entire cosmos. The universe's first superposition could have been a cosmic version of the double-slit experiment, with observation acting as the trigger that shaped reality. But here's the big question: who or what was the first observer? Some suggest it could have been a self-aware universe, a kind of cosmic consciousness. Others propose that even simple interactions between particles might count as a form of observation. Whatever the answer, Wheeler's idea forces us to rethink our place in the cosmos. We're not just passive bystanders, we might be active participants in the universe's very existence. So next time you gaze at the stars, consider this. Your act of looking might be part of an unbroken chain of observation stretching back to the birth of reality itself. The universe didn't just happen, it might have needed you to help it choose its path. Now, let's shift gears and explore a radically different take on the universe's first quantum superposition, loop quantum gravity spin networks. Unlike Wheeler's observer-driven cosmos, this theory suggests spacetime itself is stitched together from tiny, vibrating loops of quantum energy. Picture the fabric of reality not as a smooth, continuous sheet, but as a dynamic web of interconnected threads, each humming with quantum possibilities. At the heart of this idea is the notion that space isn't infinitely divisible. Instead, it's made up of discrete, grain-like units. Think of them as the pixels of the universe. These quantum loops intertwine to form spin networks, a kind of cosmic scaffolding where superposition isn't just a feature but the very foundation. In this view, the early universe wasn't a fog of probabilities waiting to collapse, it was a shimmering network of loops, each existing in multiple states at once. What's fascinating is how this ties into the birth of spacetime. According to loop quantum gravity, the universe's first superposition wasn't about particles or waves, it was about geometry. The loop's quantum states dictated how space itself could curve, stretch, and evolve. Imagine a cosmic loom weaving reality from threads that can be in two places at once, creating a tapestry where time and space emerge from quantum entanglement. This theory also offers a fresh perspective on the Big Bang. Instead of a singularity, a point of infinite density, loop quantum gravity suggests the universe might have bounced from a previous phase, with superposition smoothing the transition. It's as if the quantum loops stretched and reconfigured themselves, allowing the cosmos to reboot without tearing apart. While still a work in progress, loop quantum gravity challenges us to rethink reality at its core. If spacetime is truly woven from quantum loops, then superposition isn't just a quirk of particles, it's the hidden architecture of everything. And that means the universe's first quantum moment wasn't just a fleeting event. It was the first stitch in the fabric of existence itself. Now, let's take a step into a theory that feels like it's straight out of science fiction, but might just be science fact. The simulation argument flips everything we think we know about reality on its head. What if our universe isn't the base layer of existence at all? What if it's an incredibly advanced simulation running on some unfathomable quantum computer? And here's the kicker: superposition could be the very code that makes it all work. This idea was popularized by philosopher Nick Bostrom, who laid out a compelling case for why we might be living in a simulated reality. His reasoning goes like this: if a civilization could ever reach the technological level to create simulations indistinguishable from reality, and if they had any interest in running them, the number of simulated minds would vastly outnumber real ones. Statistically speaking, the odds that we're the original biological beings are slim. So where does quantum superposition fit in? Think of it like the ones and zeros in a computer program, except instead of binary code, the universe runs on quantum bits or qubits that can exist in multiple states at once. Superposition allows the simulation to handle infinite possibilities without crashing. Every particle, every force, even the fabric of spacetime itself could be rendered in real time by a quantum processor calculating all possible outcomes simultaneously. This theory also offers a wild explanation for some of quantum mechanics' weirdest quirks. Why does observation collapse a particle's wave function? Maybe because the simulation only renders details when they're needed, like a video game loading graphics as you explore. Why is there a speed limit to light? It could be the processor's clock speed. Even the infamous double-slit experiment, where particles act as both waves and particles, might just be the simulation optimizing its resources. Of course, not everyone buys into this idea. Critics argue there's no direct evidence yet that we're living in a simulation. But if Bostrom's right, superposition isn't just a feature of our universe. It's the foundation of its very existence, the hidden programming language of reality itself. And that raises a chilling question. If we're just lines of quantum code, who or what is running the simulation? Now, let's shift gears to a theory that blends the mysteries of quantum mechanics with something even more profound: human consciousness. Roger Penrose, the legendary physicist, teamed up with anesthesiologist Stuart Hameroff to propose a radical idea. That quantum superposition isn't just happening out in the cosmos, it's happening inside our brains, and it might be the key to consciousness itself. Their theory, called Orchestrated Objective Reduction, or ORCH for short, suggests that tiny structures in our brain cells called microtubules could be hosting quantum superpositions. These microtubules act like miniature quantum computers, processing information in ways classical physics can't explain. And here's where it gets wild. Penrose believes that when these superpositions collapse, they don't just produce random noise. Instead, they generate moments of conscious experience. But why would superposition be linked to consciousness? Penrose argues that the collapse of these quantum states isn't just a random event. It's influenced by the fabric of spacetime itself. He ties it to his earlier work on gravity's role in quantum mechanics, suggesting that consciousness might arise from the universe's fundamental physics. In other words, our ability to think, feel, and perceive could be rooted in the same quantum phenomena that shaped the early universe. Of course, this theory is far from mainstream. Critics point out that the brain is a warm, noisy place, hardly the ideal environment for delicate quantum states to survive. But Penrose and Hameroff counter that microtubules might be uniquely suited to shield quantum information, thanks to their precise structure. And if they're right, it would mean superposition isn't just a quirk of particles, it's the hidden thread weaving together mind and cosmos. So, what does this mean for the universe's first quantum superposition? If consciousness is quantum in nature, then perhaps the birth of the universe wasn't just a physical event. It was the first moment of cosmic awareness, a superposition collapsing into reality with the weight of observation. It's a dizzying thought that the universe might not just exist, but in some strange way it might also be aware. Now, let's explore a theory that turns the concept of nothingness on its head, the idea that the universe might have sprung from a state of zero energy. Imagine a cosmic balancing act where positive and negative energies cancel each other out perfectly, leaving behind a net sum of zero. This is the heart of the zero-energy universe theory, and it suggests that our entire cosmos could be the result of a quantum superposition where these opposing energies briefly tip the scales. At its core, this theory hinges on a fascinating principle from quantum physics. Particles and their antiparticles can pop into existence spontaneously, borrowing energy from the vacuum of space before annihilating each other and returning it. If you add up all the positive energy in the universe, like matter and radiation, and subtract the negative energy of gravity, the total might just equal zero. In other words, the universe could be the ultimate free lunch, emerging from a quantum fluctuation where nothingness gave way to everything. But how does superposition fit into this picture? Think of the early universe as a quantum system hovering in a state of potential, a superposition of countless energy configurations. Among them, one particular balance, where positive and negative energies perfectly offset, could have collapsed into reality, birthing the universe as we know it. This wouldn't just explain where all the energy came from, it would also hint at a deeper quantum origin for existence itself. Critics, of course, raise questions. How could such a delicate balance hold across the vast scales of the cosmos? And what triggered the collapse of this superposition? Supporters argue that quantum mechanics doesn't play by classical rules. Tiny fluctuations can have cosmic consequences, and the zero-energy state might be the most stable configuration of all. If this theory holds, it paints a breathtaking picture. The universe isn't just expanding from a singular point, but unfolding from a primordial quantum dance of energies, a superposition that chose reality over nothingness. It's a reminder that even in the void, the seeds of everything we see might have been waiting, balanced on the edge of existence. Now, let's shift our gaze to a theory that takes us beyond the familiar dimensions of space and time, the Ekpyrotic brain collision model. Picture this: our universe isn't the result of a single explosive event, but rather the aftermath of a cosmic crash between two higher dimensional membranes, or branes, floating in a vast, unseen bulk space. These branes exist in a state of quantum superposition, their possible collisions weaving the fabric of reality itself. According to this theory, the Big Bang wasn't the beginning of everything but a moment of transformation. Imagine two parallel universes, sheets of reality, drifting toward each other in a higher dimensional space. As they collide, the energy of their impact ignites the birth of our cosmos, with all its matter, radiation, and structure. The key here is superposition. Before the collision, these branes existed in a quantum haze of potential states, their paths uncertain until the moment they touched. What makes this idea so compelling is how it tackles some of cosmology's biggest puzzles. For instance, it offers an elegant explanation for the universe's startling uniformity, the fact that distant regions of space look so similar. In the Ekpyrotic scenario, the branes are stretched and smoothed before collision, like a canvas pulled taut, imprinting that smoothness onto the newborn universe. It also sidesteps the need for a singularity, that infinitely dense point at the heart of the classic Big Bang model. But how does superposition play into this? Think of the branes as quantum objects capable of existing in multiple states at once. Their collision isn't a single, predetermined event, but one outcome among many, a reality that crystallized from a sea of possibilities. This ties the Ekpyrotic model to the broader quantum landscape, suggesting that our universe's birth wasn't just a physical process but a quantum one, where probabilities became certainties. Skeptics, of course, question whether higher dimensions and colliding branes are more than mathematical abstractions. Yet proponents argue that the theory's power lies in its ability to unify quantum mechanics with gravity, a holy grail of physics, by framing spacetime as a dynamic, quantum-emergent phenomenon. If true, this model rewrites cosmic history. Our universe isn't a lone bubble of existence, but one ripple in a vast quantum ocean, where branes in superposition collide, dissolve, and rebirth realities in an endless cycle. It's a vision that stretches the imagination, revealing how deeply quantum weirdness might be woven into the cosmos. Now, let's unravel a theory that bends our understanding of time itself, the time-symmetric universe. What if the universe's first quantum superposition didn't just shape the past but was also shaped by the future? This mind-bending idea suggests that cause and effect might not be a one-way street. Instead, events in the future could ripple backward, influencing the very moment of creation. Picture the universe as a tapestry woven from both ends. In this model, superposition isn't just about multiple possibilities in the present. It's a bridge connecting past and future. Quantum particles don't merely exist in uncertain states until observed. Their final outcomes might reach back to choose their initial conditions. Imagine tossing a stone into a pond, but the ripples move both forward and backward in time, meeting in the middle to define the splash. This ties into retrocausality, the notion that future events can affect the past. Some quantum experiments already hint at this. For example, measurements made today might seem to alter a particle's behavior in the past, as if reality is adjusting itself to stay consistent. If this applies to the universe's birth, it means the first quantum superposition wasn't just a random fluctuation. It could have been guided by the cosmos. It would eventually become a cosmic handshake between beginning and end. Critics argue this sounds like science fiction, but proponents point to the math. Equations in quantum mechanics often work equally well whether time runs forward or backward. The universe's laws don't seem to care about our arrow of time. If superposition allows particles to feel out future states, why couldn't the entire universe do the same? Think of it like a sculptor chiseling a statue. Instead of starting with a block and carving toward a finished shape, the sculptor works from both the future and the past, meeting in the middle to reveal the final form. The universe's first superposition, then, might have been a dance between what was and what would be, a quantum conversation across time. This theory doesn't just challenge our sense of cause and effect. It suggests that the universe's birth wasn't an isolated moment but part of a timeless loop, where beginnings and endings are intertwined. Up next, we'll confront a paradox that takes quantum superposition to its strangest extreme, the Boltzmann brain. Stay tuned. Now, let's dive into one of the most bizarre and unsettling ideas in modern physics, the Boltzmann brain paradox. Imagine if the universe's first quantum superposition didn't just create galaxies and stars, but also spontaneous, self-aware entities floating in the void. That's the essence of this theory. According to the Boltzmann brain hypothesis, random fluctuations in the quantum foam, the seething energy at the smallest scales of reality, could by sheer chance assemble a fully conscious mind. These hypothetical brains would pop into existence, complete with false memories of a past that never happened, only to dissolve moments later. It's like a cosmic glitch where the universe briefly hallucinates a thinking being. How does superposition fit in? Quantum mechanics allows particles to exist in multiple states until observed. In an infinite or near-infinite universe, the math suggests it's not just possible but inevitable that some of these superpositions would accidentally arrange themselves into complex, self-aware structures. The odds are astronomically low, but given enough time and space, even the most improbable events become certain. Critics argue this idea is absurd. Why would the universe bother creating isolated minds instead of the orderly cosmos we see? But proponents counter that it's a natural consequence of entropy and probability. If reality is just a vast quantum soup, then Boltzmann brains are simply statistical inevitabilities, no weirder than the fact that we exist at all. Here's the twist: if Boltzmann brains are more likely than entire universes, how do we know we're not one of them? Maybe everything you remember, your life, the world, even this video, is just a fleeting illusion conjured by quantum chaos. It's a dizzying thought, but it forces us to ask, what does it mean to be real in a universe built on superposition? Next up, we'll venture into an even more radical idea, that our entire universe might be hiding inside a black hole. Stay curious. Now, let's take a step into the unknown and explore a theory that turns our understanding of the cosmos inside out, literally. Picture this. What if our entire universe isn't just floating in space, but is actually hidden inside a black hole? That's the mind-bending premise of the black hole universe theory. Here's how it works. Black holes are regions where gravity is so intense that not even light can escape. But what happens to all that matter and energy that gets sucked in? Some physicists suggest it doesn't just vanish. Instead, it could spawn an entirely new universe inside the black hole's singularity, the point where the laws of physics break down. In this scenario, our universe might be the interior of a black hole from a parent universe, with its own set of physical laws born from quantum superposition. Quantum superposition plays a key role here. At the singularity, particles wouldn't just exist in one state, they'd be in a blur of all possible states simultaneously. This chaotic quantum soup could collapse into the stable reality we know today, creating space, time, and everything in between. It's like the universe booted up from a quantum glitch, with superposition as its operating system. Critics ask, how could we ever prove this? After all, we can't peek beyond a black hole's event horizon. But supporters point to clues in our own universe, like the uniformity of the cosmic microwave background or the way galaxies are distributed. These patterns might be echoes of the black hole's quantum origins, hints that our cosmos was forged in the heart of a singularity. The implications are staggering. If every black hole births a new universe, then our reality might just be one link in an endless chain of cosmic nesting dolls. And if superposition governs these singularities, then the very fabric of existence could be a quantum accident, a fleeting state that somehow stuck around long enough for us to ponder it. Next, we'll unravel how quantum states might have selected the universe's classical properties, shaping the reality we take for granted. Stay with us, the journey gets even wilder. Now, let's shift gears to a theory that flips the script on how our universe settled into the reality we recognize. Imagine a cosmic game of survival where only the most stable quantum states get to stick around. That's the heart of the quantum Darwinism model. Here's the idea. In the early universe, particles weren't just in one state, they existed in a blur of countless possibilities thanks to quantum superposition. But somehow, this quantum chaos crystallized into the predictable, classical world we see today. Quantum Darwinism suggests that certain states were selected because they were more resilient, like the fittest in a quantum survival contest. Think of it like a crowd shouting all at once. Over time, only the loudest, clearest voices, those that could be heard over the noise, shaped what everyone else repeated. In the same way, the universe's quantum states competed, and the ones that could withstand decoherence. The process that collapses superposition became the building blocks of reality. These winning states left imprints like footprints in cosmic sand that we now observe as the laws of physics. What's fascinating is how this mirrors biological evolution. Just as natural selection favors traits that help organisms survive, quantum Darwinism proposes that the universe favored states that could persist and propagate. This might explain why we don't see quantum weirdness in everyday life. Only the most stable, classical outcomes made the cut. Critics argue this raises a chicken and egg question. How did the selection rules themselves emerge? But supporters point to experiments showing how quantum systems naturally prefer certain states when interacting with their environment. It's as if the universe has a hidden bias toward order, sculpted by quantum competition. Up next, we'll dive into a theory that suggests reality might be far stranger and more interconnected than we ever imagined. The journey through quantum mysteries is far from over. Now, let's peel back another layer of quantum mystery with a theory that challenges our very notion of reality. David Bohm, a physicist who dared to think differently, proposed that the universe operates on two levels: the surface world we see and a hidden, deeper reality he called the implicate order. Here's the twist. In Bohm's view, quantum superposition isn't just a quirk of particles, it's the universe's default setting. Beneath the apparent chaos of our everyday world lies an ocean of interconnected possibilities, where everything is folded together in a state of pure potential. What we perceive as separate objects or events are just temporary unfoldings of this deeper, unified reality. Think of it like a hologram. If you shatter a holographic plate, each fragment still contains the entire image, just from a different angle. Similarly, Bohm suggested that every part of the universe carries information about the whole, with superposition acting as the glue that binds it all together. This hidden order isn't random, it's guided by what Bohm called hidden variables, subtle forces that steer quantum behavior behind the scenes. Critics dismissed this as unnecessary complexity, arguing that mainstream quantum mechanics works fine without hidden layers. But Bohm's ideas gained traction when experiments revealed eerie quantum connections, like entangled particles responding instantly to each other across vast distances, as if they were still part of that deeper, folded reality. What makes this theory so compelling is how it reframes the universe's first superposition. Instead of a fleeting quantum fluke, superposition becomes the eternal foundation of existence, with our classical world merely a ripple on its surface. It's a reminder that reality might be far richer and far stranger than we ever imagined. Next up, we'll explore how spacetime itself might be woven from quantum threads, revealing yet another astonishing layer to our cosmic story. The mysteries only deepen from here. Now, let's step into a radically different perspective, one where spacetime isn't smooth and continuous, but built from tiny, indivisible building blocks. This is the heart of causal set theory, a framework that reimagines the fabric of reality as a vast network of discrete atoms of spacetime, each existing in a quantum superposition before snapping into place. Picture the universe as a cosmic mosaic. Instead of a blank canvas, imagine trillions of microscopic tiles, each representing a fundamental unit of spacetime. In their earliest state, these tiles weren't fixed. They flickered in and out of superposition, a shimmering sea of potential. But as the universe cooled, something extraordinary happened. Those quantum possibilities froze into a specific arrangement, like crystals forming in a cooling liquid. This crystallization didn't just create space and time, it defined them, with each tile's position determined by its causal relationship to others. Here's where it gets mind-bending. In causal set theory, the order of events isn't dictated by a pre-existing timeline. Instead, time emerges from the connections between these spacetime atoms. Think of it like a domino chain. The dominoes don't move until one tips into the next, creating the illusion of sequence. Similarly, our experience of past, present, and future could just be the universe's way of reading the pattern of these quantum links. Critics argue that the math is still evolving, but supporters point to its elegant solution to a thorny problem: infinity. By replacing the smooth, infinite spacetime of general relativity with finite quantum steps, causal set theory sidesteps the singularities that break other models. It's as if the universe traded a bottomless pit for a staircase, one quantum step at a time. What does this mean for the first superposition? If causal set theory holds, then the universe didn't just have a quantum beginning, it was a roiling quantum network waiting to crystallize into the cosmos we know. And just like that, we've uncovered another clue in the mystery of how something as vast as spacetime could emerge from the tiniest of quantum whispers. Next, we'll see how these quantum threads might weave together into an even more astonishing pattern, a dynamic, ever-changing graph that could rewrite the rules of reality itself. The journey into the quantum unknown continues. Now, let's stretch our imaginations even further with a theory that turns spacetime into something resembling a cosmic game of connect the dots. This is the quantum gravity hypothesis, where the universe isn't just made of discrete pieces, it's a living, shifting web of quantum connections. Imagine spacetime as a vast, ever-changing network, like a social media platform for the cosmos. Instead of static points, every node in this network is in a constant dance of superposition, flickering between possible connections. In the earliest moments, this graph wasn't rigid. It was a fluid, quantum soup of potential links. Then, as the universe cooled, those connections froze into place, much like water turning to ice. The pattern that emerged didn't just create space and time, it became space and time. Here's the twist. In this model, the speed of light isn't a fundamental constant. It's a consequence of how densely connected this quantum graph is. Think of it like traffic on a highway. Fewer connections mean faster travel for information, mimicking what we observe as light speed. But in the gravity hypothesis, this could change over time or even in different regions of space, hinting at a universe far more flexible than Einstein imagined. Critics question how this abstract network translates to the tangible world we experience, but proponents argue it solves a major puzzle: how gravity and quantum mechanics might finally shake hands. By treating spacetime as a dynamic graph, the theory naturally avoids the infinities that plague other models, offering a fresh path to unifying physics. So what does this mean for the universe's first superposition? If quantum gravity is right, then the Big Bang wasn't just an explosion. It was the moment this cosmic web chose its configuration from a sea of quantum possibilities. And just like that, we're staring at yet another breathtaking answer to how reality might have stitched itself together from the quantum void. Next, we'll dive into a theory so bold it suggests the fabric of spacetime is held together by something even stranger: quantum entanglement itself. The deeper we go, the more the universe reveals its hidden threads. Now, let's untangle one of the most mind-bending ideas in modern physics: a theory that stitches together two seemingly unrelated phenomena into a single cosmic tapestry. This is the AR equals EPR conjecture, where the strange magic of quantum entanglement might actually be the secret ingredient holding spacetime itself together. Picture two particles entangled across vast distances, instantly influencing each other no matter how far apart they are. That's the EPR part, named after Einstein, Podolsky, and Rosen, who first highlighted its weirdness. Now imagine a wormhole, a tunnel through spacetime connecting two distant points. That's the ER part, courtesy of Einstein and Rosen. At first glance, these ideas couldn't seem more different. But what if they're two sides of the same coin? Here's where superposition comes in. The conjecture suggests that every pair of entangled particles is secretly linked by a microscopic wormhole, a bridge forged from quantum uncertainty. In this view, entanglement isn't just spooky action at a distance, it's spacetime's way of staying stitched together. And if that's true, then the universe's first superposition wasn't just a random quantum fluke. It was the moment these hidden threads began weaving the fabric of reality itself. Critics argue this idea is more metaphor than math, but supporters point to breakthroughs in string theory and holography that hint at a deeper connection. If spacetime emerges from entanglement, it could explain why the universe looks smooth and continuous despite being built from quantum grains. It's as if the cosmos is a vast network of entangled relationships, with superposition acting as the invisible glue. So what does this mean for the Big Bang? If ER equals EPR is correct, then the universe's birth wasn't just a quantum event. It was the ultimate entanglement, a cosmic knot tying everything into existence. And just like that, we're left staring at a universe where the threads of reality might be far more connected than we ever dreamed. Next, we'll explore a theory that turns time itself into a quantum illusion, where the past and future might not be as fixed as they seem. The deeper we look, the more the universe defies our everyday intuition. Now, let's step into a realm where time itself might be nothing more than a cosmic mirage. The thermal time hypothesis flips our everyday understanding of time on its head, suggesting it's not a fundamental feature of the universe but an illusion born from quantum superposition. Imagine a universe before time existed, a timeless quantum soup where everything exists in a blur of possibilities. In this view, time isn't a ticking clock but a side effect of quantum systems interacting and decohering. Think of it like steam rising from a hot cup of coffee. The steam isn't a thing itself, it's just how we perceive the heat's energy escaping. Similarly, time might be our way of perceiving the universe's quantum dance, a thermal glow from the deeper, timeless reality beneath. This idea ties back to superposition in a fascinating way. If the universe began in a quantum haze where all states coexisted, then the emergence of time could be the moment those states started cooling into the world we recognize. It's as if reality froze out of the quantum foam, leaving time as its ghostly footprint. Some physicists even suggest that entropy, the universe's tendency toward disorder, might be the engine driving this illusion, with superposition providing the raw material. Critics argue this reduces time to a statistical trick, but supporters counter that it solves deep puzzles like why time only moves forward. If time is thermal, then its arrow might just point the way heat does, from hot to cold, order to chaos. And if that's true, then the universe's first superposition wasn't just a quantum event. It was the spark that lit time's fuse. Next, we'll dive into a theory where reality itself might be a matter of personal perspective, reshaping how we see the universe's quantum foundations. The deeper we go, the stranger and more wondrous it all becomes. Now, let's shift our perspective to something even more personal: how your own beliefs might shape the universe itself. Quantum Bayesianism, or cubism, takes the weirdness of quantum mechanics and makes it deeply human. This theory suggests that probabilities in quantum superposition aren't just cold, hard facts of nature, they're reflections of our personal beliefs about what's possible. Think of it like betting on a coin toss. Before the coin lands, you might say there's a 50-50 chance of heads or tails. But that probability isn't a property of the coin, it's your own uncertainty about the outcome. Cubism applies this idea to the quantum world. When a particle exists in superposition, being both here and there at once, the probabilities we assign to its states aren't inherent to the particle. They're our way of making sense of the unknown, like placing bets on reality itself. This flips traditional quantum theory on its head. Instead of superposition being an objective feature of the universe, cubism says it's a tool for observers to navigate a world full of quantum ambiguity. The universe doesn't collapse into one state, it's your interaction with it that makes one outcome feel real to you. Some physicists argue this solves the infamous measurement problem by putting the observer front and center. After all, if probabilities are personal, then the universe's first superposition wasn't just a cosmic event. It was the moment observation began weaving reality from possibility. Critics call cubism too subjective, but supporters fire back. Isn't all science, at some level, a conversation between us and the universe? If cubism is right, then the birth of reality might not have been a grand explosion but a quiet agreement, a handshake between quantum uncertainty and the minds that try to understand it. Next, we'll uncover a geometric twist in the quantum story, where the universe's deepest secrets might hide in an elegant mathematical shape. The mystery only deepens from here. Now, let's take a step into the world of geometry, where the universe's quantum secrets might be hiding in plain sight. Meet the amplituhedron, a dazzling mathematical shape that's rewriting how we understand particle interactions, and it all ties back to superposition. At first glance, the amplituhedron looks like an abstract sculpture, but it's actually a revolutionary tool for physicists. Traditionally, calculating how particles collide and interact required mind-numbing complexity, with endless Feynman diagrams and probabilities. But the amplituhedron cuts through the noise. It simplifies these calculations into a single geometric object, where the volume of its facets directly encodes the outcomes of particle collisions. Here's where superposition comes in. The amplituhedron doesn't just describe particles as fixed entities, it treats them as quantum possibilities, existing in multiple states at once. Think of it like a cosmic kaleidoscope, where every twist reveals a new configuration of reality. This suggests that superposition isn't just a quirk of quantum mechanics. It might be the foundational language of the universe written in geometry. Some theorists even argue that the amplituhedron hints at a deeper truth, that spacetime itself could emerge from a quantum network of superposed connections. If that's the case, then the universe's first superposition wasn't just a fleeting moment. It was the birth of a geometric code that still shapes everything from atoms to galaxies. Of course, not everyone is convinced. Critics point out that the amplituhedron, while elegant, hasn't yet been tested in all scenarios, but its very existence challenges us to rethink reality. Could the cosmos be less like a machine and more like a puzzle, where superposition is the glue holding the pieces together? Next, we'll venture into the holographic frontier, where the boundary of the universe might hold the key to its deepest mysteries. The journey is far from over. Now, let's peel back another layer of cosmic mystery with a theory that turns our understanding of reality inside out. Imagine the universe as a hologram where everything we see, stars, galaxies, even space and time, is actually encoded on a distant two-dimensional surface. This is the heart of the AD-SCFT correspondence, a groundbreaking idea that suggests our three-dimensional world might just be a projection from a quantum boundary. Here's how it works. In this framework, the boundary, called the CFT, or conformal field theory, acts like a cosmic hard drive, storing all the information about the universe's interior, known as the AD-S, or anti-de Sitter space. What's mind-blowing is that quantum superposition plays the role of the translator between these two realms. The boundary's tangled web of quantum states, existing in multiple configurations at once, could holographically generate the depth and complexity of the universe we inhabit. Think of it like a movie projected onto a screen. The images appear three-dimensional, but they're really just flat pixels obeying precise rules. In the same way, the AD-SCFT correspondence implies that gravity, particles, and even the fabric of spacetime might emerge from quantum superpositions dancing on the edge of reality. This isn't just science fiction. Physicists like Juan Maldacena have shown mathematically how this duality could solve long-standing puzzles, like uniting quantum mechanics with Einstein's theory of gravity. But here's the twist. If the universe is truly holographic, then its very first quantum superposition wasn't just a fleeting event. It was the moment the cosmic code booted up, setting the rules for how information on the boundary shapes the bulk. Critics argue that testing this idea is notoriously difficult, since the AD-S space it describes is an idealized mathematical playground. Yet, the mere possibility forces us to ask, is our universe's vastness just a shadow of something far simpler, written in quantum ink at the edge of everything? Next, we'll dive into an even stranger idea where the fabric of spacetime might share eerie similarities with the quantum quirks of exotic materials. The universe's secrets keep getting curiouser. Now, let's take a detour into the lab where the bizarre behavior of exotic materials might hold clues to the universe's deepest secrets. Picture a superconductor, a material that lets electricity flow without resistance when chilled to frigid temperatures. At this quantum phase transition, electrons pair up and move in lockstep, as if they've become a single, coordinated entity. What if spacetime itself undergoes a similar transformation? This is the wild premise of Theory 23, where physicists draw startling parallels between the quantum quirks of condensed matter and the fabric of the cosmos. Just as superconductivity emerges from electrons collapsing into a unified state, spacetime might have crystallized from a primordial quantum soup via superposition. Think of it like ice forming from water, a sudden shift in organization that changes everything. In the early universe, a phase transition could have locked quantum superpositions into the stable structure we now call reality. The math behind this idea is surprisingly elegant. Exotic materials like topological insulators exhibit edge states that are robust against disturbances, much like how spacetime seems smooth and continuous despite its quantum roots. Some researchers, like Xiao Gangwen, propose that spacetime's very geometry could be an emergent property arising from entangled quantum states in a hidden lattice, a cosmic version of how magnetism emerges from atomic spins. Critics point out that scaling up lab observations to cosmic proportions is a leap, but the tantalizing similarities are hard to ignore. If true, the universe's first superposition wasn't just a flicker. It was the moment reality froze into the phase we recognize. Next, we'll explore an even more radical notion, that the universe runs on quantum information with superposition as its binary code. The deeper we dig, the more the cosmos feels like a puzzle written in quantum shorthand. Now let's shift gears and dive into a mind-bending idea. What if the universe isn't made of matter or energy, but pure information? This is the core of Theory 24, where physicists suggest reality itself might be a cosmic computer running on quantum bits. Imagine the universe as a vast, intricate code, with superposition acting like the ones and zeros of existence. At the heart of this theory is the bold claim that everything, particles, forces, even space-time, is just information processing. Superposition, then, isn't just a quantum quirk. It's the fundamental language of reality, where every possible state exists until measured or computed into being. Think of it like a cosmic hard drive, storing every potential outcome until the universe reads the data and collapses it into what we perceive. Pioneers like John Archibald Wheeler famously declared, "It from bit," suggesting that physical reality arises from information. In this view, the Big Bang wasn't just an explosion of matter. It was the first cosmic algorithm booting up with superposition as its foundational operation. Even black holes, those enigmatic devourers of stars, might be nature's ultimate data compressors, squeezing information into unimaginably dense bits. Critics argue this reduces the richness of existence to cold, digital logic. But supporters counter that it elegantly unifies physics, linking quantum mechanics, gravity, and thermodynamics under one framework. After all, entropy, the measure of disorder, mirrors information loss, and quantum entanglement looks a lot like data sharing across cosmic distances. So, is the universe a quantum computer? If so, superposition isn't just a feature, it's the very fabric of reality, weaving the code of existence itself. Next, we'll uncover how ghostly particles from the dawn of time might still carry echoes of that primordial quantum state. The deeper we look, the more the cosmos feels like a grand equation waiting to be solved. Now, let's turn our attention to the ghostly messengers of the cosmos, neutrinos. These nearly massless particles, born in the fiery chaos of the early universe, might hold the key to unlocking one of quantum mechanics' greatest mysteries. Theory 25 proposes that the cosmic neutrino background, a faint relic from the universe's infancy, could still carry traces of its primordial quantum superposition. Neutrinos are famously elusive, passing through entire planets like they're not even there. But their very strangeness makes them perfect candidates for preserving quantum weirdness. In the first moments after the Big Bang, neutrinos existed in a fog of superpositions, their states entangled across the newborn cosmos. As the universe expanded and cooled, most quantum effects collapsed into the classical reality we know today. But neutrinos, barely interacting with anything, might have avoided this fate. Think of them as cosmic time capsules. While photons from the early universe were scrambled by collisions, neutrinos sailed through untouched. If superposition left any fingerprints on them, those marks could still be hidden in their subtle vibrations. Detecting this would be like finding a whisper from the universe's first quantum breath. Experiments like the upcoming Ptolemy project aim to catch these ancient neutrinos, hoping to spot anomalies that betray their quantum origins. Skeptics argue that decoherence, the process that destroys quantum superpositions, would have erased any such signatures over billions of years. But if neutrinos did preserve even a faint echo of superposition, it would revolutionize our understanding of quantum mechanics' role in shaping reality. So, are neutrinos the universe's oldest quantum relics? The answer might be hiding in their silent, ghostly dance across space and time. Next, we'll explore how the arrow of time itself could be tied to the collapse of the universe's first superposition, a twist that redefines cause and effect. Now, let's unravel one of the most mind-bending connections in quantum cosmology, the link between time's arrow and the universe's first superposition. Theory 26 suggests that the very direction of time, the reason we remember the past but not the future, might be rooted in the collapse of that primordial quantum state. Picture this: in the early universe, everything existed in a blur of possibilities, a superposition where cause and effect hadn't yet taken shape. Then, as quantum decoherence kicked in, that fuzzy quantum reality crystallized into the orderly universe we know. But here's the twist: this collapse didn't just create space and matter, it might have also set time's irreversible flow into motion. Think of it like a cosmic hourglass. Before superposition collapsed, time was symmetrical with no clear past or future. But the moment quantum probabilities resolved into definite states, time gained its arrow, forever pointing forward. This idea flips traditional physics on its head, proposing that time's direction isn't just a byproduct of entropy, but a direct consequence of quantum mechanics' foundational moment. Some physicists argue that without this collapse, the universe would lack the asymmetry needed for time to flow. Others counter that entropy alone explains time's arrow. But if the quantum origin theory holds, it would mean our experience of time from aging to memory is ultimately tied to that first cosmic decision. So, was the birth of time itself a quantum event? The answer could rewrite not just cosmology, but our understanding of reality's deepest fabric. Up next, we'll dive into how unbroken supersymmetry in the early universe's superposition might have seeded the very laws of particle physics. Now, shifting our gaze to the cosmic blueprint of matter itself, let's explore how the universe's first quantum superposition might have hidden a secret symmetry, one that could explain the very building blocks of reality. Theory 27 proposes that before the cosmos settled into the laws we know today, it existed in a state of perfect supersymmetry where every particle had a hidden twin. Imagine the early universe as a grand, unbroken mirror. For every quark there was a squark, for every electron a selectron. These superpartners weren't just theoretical, they were woven into the fabric of quantum superposition, dancing in perfect balance. But as the universe cooled and superposition collapsed, this symmetry shattered, leaving behind the lopsided particles we observe now. Here's why this matters: supersymmetry isn't just elegance for elegance's sake. It could solve some of physics' biggest puzzles, like why gravity is so weak compared to other forces, or what makes up dark matter. If the primordial superposition preserved this symmetry even briefly, it might have imprinted clues in today's particle collisions or cosmic rays. Critics argue we've yet to find proof of superpartners in accelerators like the Large Hadron Collider, but supporters counter that these particles could be far heavier than expected, their traces lingering in the universe's quantum infancy. Either way, the idea that superposition once cradled a flawless symmetry and its breakdown-shaped physics offers a tantalizing glimpse into nature's deepest patterns. So, was supersymmetry the universe's first great symmetry, lost in the quantum dawn? The answer might lie in the echoes of that primordial superposition. Next, we'll venture into a daring idea that universes themselves evolve through quantum selection inside black holes. Now, let's take a leap into a theory that turns black holes into cosmic cradles. Theory 28 introduces Lee Smolens's radical idea that universes might actually evolve, much like living organisms, through a process of quantum selection inside black holes. Picture this: every time a black hole forms in our universe, it could be birthing an entirely new cosmos in its depths. But here's the twist: these baby universes don't just pop into existence randomly. Instead, they inherit traits from their parent universe, tweaked by the quantum superposition that governed their birth. Over countless generations, universes that produce more black holes and thus more offspring would dominate the cosmic landscape. This isn't just science fiction. Smolens's theory suggests that the laws of physics we observe today might be the result of a kind of cosmic Darwinism. Universes fine-tuned to create black holes would thrive while others fade into oblivion. It's a staggering thought. The very constants of nature, like the strength of gravity or the mass of an electron, could be the product of an evolutionary arms race spanning eternity. Critics question how this process could ever be tested, but supporters point to subtle clues. If our universe is optimized for black hole production, we might find unexpected patterns in their distribution or properties. Others argue that quantum superposition at the moment of a black hole's collapse could leave fingerprints in the fabric of spacetime itself. Whether this theory holds up or not, it forces us to rethink our place in the cosmos. Are we just one link in an endless chain of universes, each shaped by the quantum quirks of its ancestors? The answer might lie in the silent depths of black holes, where superposition could still be weaving new realities. Next, we'll explore an even more mind-bending possibility, that the universe's first superposition needed a conscious observer to bring it into existence. Now, let's venture into one of the most provocative ideas yet. What if the universe needed a mind to bring it into being? Theory 29 takes us down the rabbit hole of quantum consciousness, suggesting that the very first superposition of the cosmos couldn't have collapsed into reality without an observer. This idea flips traditional physics on its head. In quantum mechanics, particles exist in multiple states until measured, a concept famously illustrated by Schrödinger's cat, both alive and dead until someone checks the box. But what if this rule doesn't just apply to tiny particles? What if the entire universe began as a haze of possibilities, waiting for a conscious observer to pin it down? Some physicists, like John Wheeler, argued that reality is participatory. It doesn't exist in a definite state until it's observed. Extend that to the Big Bang, and you get a wild implication. The universe's birth might have required a primordial form of consciousness to choose its initial conditions. This isn't about humans looking at the cosmos, it's about some fundamental awareness woven into the fabric of existence itself. Critics dismiss this as philosophy masquerading as science, but supporters point to the eerie fine-tuning of the universe. Why do the laws of physics allow for life? Could consciousness be not just a product of the universe, but a prerequisite for its existence? The debate rages on, with some even linking this idea to quantum biology, where processes in our brains might exploit quantum effects. Whether you find this theory inspiring or outlandish, it forces us to ask profound questions. Is the universe a cold, mechanical accident, or does consciousness play a starring role in its story? Next, we'll confront the ultimate cosmic question: what if everything began from absolute nothingness? Now, let's take one final leap into the unknown. What if the universe didn't just emerge from something, but from nothing at all? Theory 30, the Null Universe Hypothesis, pushes the boundaries of imagination by proposing that everything we know could be a fleeting quantum fluctuation in an infinite sea of nothingness. Picture this: a perfect void, completely empty, not even space or time. Yet, according to quantum mechanics, even nothingness isn't truly empty. At the tiniest scales, particles flicker in and out of existence, borrowing energy from the vacuum before vanishing again. What if the universe itself was born from one of these fleeting quantum events? A momentary blip in the void that, against all odds, stabilized and expanded into the cosmos we see today. This idea ties back to superposition. The universe's initial state could have been a quantum haze of possibilities, a mix of something and nothing, until one path crystallized into reality. Some physicists argue that the laws of quantum mechanics allow for this spontaneous creation. No divine spark or external cause required. It's as if the universe bootstrapped itself into existence, with superposition acting as its cradle. Of course, this raises mind-bending questions. How can something come from nothing? Why did this particular fluctuation lead to a universe that lasts billions of years rather than vanishing instantly? Supporters of the Null universe hypothesis point to the zero-energy balance of the cosmos, the idea that the positive energy of matter and the negative energy of gravity cancel each other out, making the total energy of the universe zero. In a way, the universe might still be nothing, just an elaborate rearrangement of zero. Critics counter that this theory swaps one mystery for another, leaving the origin of quantum laws unexplained. But whether you find it elegant or unsatisfying, the Null universe hypothesis forces us to confront the deepest question of all: why is there something rather than nothing? And with that, we've reached the end of our journey through 30 groundbreaking theories about the universe's first quantum superposition. From the Big Bang as a quantum event to cosmic consciousness and the void itself, each idea challenges our understanding of reality in its own way. So, which theory resonates with you? Drop your thoughts in the comments below, and don't forget to subscribe for more mind-expanding explorations of the cosmos. The universe is full of mysteries. Let's keep unraveling them together. As we wrap up this cosmic journey, it's astonishing to see how 30 wildly different theories all point to one mind-bending idea. Quantum superposition might be the key to unlocking the universe's greatest mystery, its very birth. From the Big Bang as a quantum fluctuation to the universe springing from absolute nothingness, each theory paints a unique picture of reality's fragile, shimmering origins. What's remarkable is how these ideas don't just challenge our understanding of the cosmos, they shatter it, revealing a reality far stranger and more interconnected than we ever imagined. Think about it, superposition isn't just a quirk of tiny particles. It could be the cosmic blueprint, the hidden thread weaving through everything from the birth of spacetime to the existence of parallel worlds. Whether you're drawn to the holographic universe, the simulation hypothesis, or the daring null universe idea, one thing's clear: our classical intuition falls short when faced with the quantum foundations of existence. So, which of these theories speaks to you? Maybe it's the elegance of a zero-energy universe, or the haunting possibility of Boltzmann brains. Or perhaps you're still wrestling with the biggest question of all: why there's something rather than nothing. Whatever your take, the conversation doesn't end here. Drop your favorite theory in the comments below, and let's keep the debate alive. If your mind's buzzing with more questions, you're in the right place. Hit that subscribe button and ring the notification bell. We're always diving deeper into the universe's wildest mysteries. From quantum riddles to cosmic enigmas, there's always another layer to explore. Thanks for joining this adventure through the quantum origins of everything. Until next time, keep questioning, keep wondering, and remember, reality is far stranger than we think.